Hello everyone! It's Saturday once again. Which means, very importantly, that it's another Get Into Mathematical Logic Day. Last week, we introduced our first fully syntactic system for our notion of syntactic logical consequence or proof, in which we declared that something was going to be a logical consequence of something else if you could produce a string of symbols such that you either started with nothing or you started with a set of declared premises, and through the mechanic computational use of precise abstract rules produced a sequence of transformations of formulas that ended with the desired formula. And this desired formula that is at the end of the sequence we call the conclusion, and the formulas that are present by being explicitly presented as premises are, well, obviously, they're premises. We also saw that if I could produce a sequence of symbols that started with 0 premises, then everything produced at the end of this sequence that has no premises is not just a conclusion, it's a theorem of our system. That is something that is unconditionally present or valid in our system. We went over our 12 basic rules. There's one for each or 5 connectives, one for introduction and one for elimination. Even though we're not really eliminating the formula, we're just analyzing them or breaking them down. And we have 2 special rules that deal with contradictions. One is to allow us to insert the symbol of contradiction, an upside down T. And the other was to extract any formula from the contradiction symbol. Hello, Bones! How are you doing? Hope you're having a passable 4th of July. So, yeah, we went over those rules and we did some exercises. And through those exercises, we approach in a very basic way the kind of experience that real mathematicians do. Very strong emphasis on approaching. It's just like a baby-like example of what real mathematics is like. Real mathematics is not crunching numbers. Real mathematics is not making really big and long multiplication and divisions. It's more about creating proofs that explore this structure and the relationships of various axiomatic systems. And speaking of, we have the homework. In which I ask for 10 arguments to be proven. Except the really 9, we'll get into it as that. First, we have a relatively simple exercise. We have P and Q, and we want Q and P. This, as we'll show later on today, is it's the commutation property of the conjunction. Bones says Oli, ando jugando Dota, obviously. Pero vi la notificación y quise pasarlo a saludar. Ah, ok. Gracias por pasar a saludar, Bones. Te deseo mucha suerte en tu Dota, que ganes mucho. Yeah, so this is the commutation property for the conjunction, which basically means that if you have P and Q, you can also have Q and P. We'll prove this as a general rule in a bit. The proof for this specific case is rather simple because our conjunction introduction rule is already commutative. It just says if you have two, you can select the order. So instead of going 2, 3, we just went 3, 2, and that's it. We first break down P and Q from P and Q. So we have P from conjunction elimination at 1, Q from conjunction elimination at 1, and then we put them back together, but in the symmetric order. Q and P instead of P and Q. Then we have proof of, if we have P and Q, then we should prove P if and only if Q. It makes sense. Recall the truth table. The truth table says that P if and only if Q is true when either P and Q or not P and Q. So if we have one of these, we can just add by disjunction, introduction, the other, and that is our rule of biconditional introduction in the second form, pasted over here. Now we have something tricky. We know that P if and only if Q is equivalent to not P if and only if Q. They are interpreted in the same way. They have the same values. They are equivalent. But we are not in a semantic context. We're in a syntactic context. We need to prove this with our step-by-step rules. So there are two ways to do this. I did both. The first one is to generate this. So look at the biconditional introduction rule. It says any formula, alpha and beta, or not alpha and beta. Any formula or its negations. In this case, not P is alpha. Remember that when we use metavariables, a metavariable stands for any well-formed formula of our language. And not P is a well-formed formula for language. Therefore, if I want not P if and only if not Q, I need this structure, but instead of alpha, I need not P and not Q. And here I need the formula with a negation. I can separate it visually if there's need for clarity. So, all of this will be not alpha. So we need not alpha negated. In this case, it's just not P. Same with not Q. Now, last week we proved the equivalence of the double negation, which we can use as a rule. Basically, it means that any well-formed formula for language is equivalent to that well-formed formula with two negations stacked or removed. It can go both ways. And something special about these equivalence rules is that they can be applied to the parts of formula, unlike the basic introduction and elimination rules. So I can just stick not P to P and not Q to Q. Double negation at 1, double negation at 2. And then I add this side through introduction of the disjunction at 3, and that is enough for the introduction of the conditional rule. Now, if that is not persuasive, it's fine. I did it without using the double negation rule. Without the double negation rule, I have to do the following. I will use this aspect of the biconditional introduction rule. So we'll prove that not P implies not Q, and not Q implies not P. So because I have P and Q, as soon as I create a soft proof by hypothesis of P, or not P, sorry, I have a contradiction, which I introduce by 2 and 3, P and not P, which allows me to produce any formula I want, in this case not Q, so not P implies contradiction, and contradiction implies not Q, so indirectly not P implies not Q. And the case is perfectly symmetrical with not Q. As soon as I create a subproof with with not Q, I get a contradiction, and from that I can generate not P. So P implies not Q implies not P. I have both conditionals with both its elements negated, which means I can generate not P if and only if not Q. The next exercise is a bit of a troll. I usually leave one invalid exercise in the new homeworks I give. A particularly easy to spot invalid exercise. How do we know this one is invalid? Because it asks us to prove Q and T. And in 2 and 3, we get all of the ingredients we need to get T. We have a conditional and we have the antecedent. So we can get T by modus ponens, or conditional elimination. But I have P, therefore Q, or if P then Q, but I don't have P. I don't have anything to analyze this conditional, so I will never be able to get Q. So I give you the structure that works. Hello, Jair, for becoming a Samigo. Welcome in. Yeah, so you have all the ingredients to make a valid conditional elimination or modus ponens. Hello, Rupert. How you doing? Was getting through the VODs through this week while my brain regenerates. Valid. Just a reminder, all the VODs of the Getting to Mathematical Logic series are on YouTube. Let me link the playlist. Is this Boolean algebra? Yes, it is. Yes, it is. It's very basic Boolean algebra for people who want to get into mathematical logic. Let me share the playlist. Where's the logic gates? We already did the logic gates. We are in the syntactic aspect of the system, of the proposition logic system. We define the logical connectives, aka the logic gates, earlier. Let me share the playlist. It's missing the video from last week. I think it's uploaded. I just haven't put it in the playlist. Yeah. It is my latest video on my channel. It's just not in the playlist, but I'm gonna play it. Exclusive or and XOR NOR. We are not using exclusive or XOR, but we're using the disjunction as or. We're using the conjunction as and. We're using the weird sideways L as not. And with those three, we can produce NAND, NOR, and XNOR if you want to. For example, NAND is not AND. So not AND will be this. We can, oh, okay, no, that got turned into an emoji. There we go. So not AND can be produced by a clever use of the conjunction and negation. And I guess you can all guess how you can produce NOR. NOR means not or. So we can produce that with a disjunction and a negation. XNOR is actually equivalent to this. No, wait. This is XOR. No, wait, no. This is XNOR, yeah, this is XNOR. Yeah, exactly. This is XNOR. Yeah, that's not all right. Yeah, exactly, which will make it equivalent to NOR. And XOR is just the biconditional negated. And we can prove this very quickly with a very simple truth table. Let me make some spaces. True, false, false, true, false. So this symbol, this biconditional, we use as material equivalence. It's true when both inputs are true, so it's true here. And it's false when they are different, so it's false here. It's different, so it's false. They're the same, so true. And the negation inverts, so we get FTTF. Which is the truth table of XOR, or exclusive OR. One or the other, but not both. I recommend using more detailed explanations, using plain English rather than symbols, because newcomers... Yeah, that's the thing though. This is the 7th session. We've had 6 sessions previous to this one. So I know it's a bit of an imposition to just people to just watch the VODs. But yeah, if you want a more thorough explanation, we went over the logical connectives in the second and third videos that are linked up above. So yeah, we don't need dedicated symbols for NOR, NAND, and XNOR. We can produce them with our 5 logical connectives. In fact, we didn't prove it, but soon we'll be able to. We can prove that with our 5 logical connectives, we can represent all possible states in a Boolean algebra. That means that our set of symbols is complete. Anyways, back to the homework. Yeah, in this, yep, exactly. Yep, that produces NAND. Yeah. The other thing, Rupert, is that this is not a graded course. There is no time. That's something I like about online teaching, as opposed to in-person courses. I mean, there's a time and place for in-person college courses. Some people work under that structure. They like the pressure, they like the order, they like the discipline. But some people don't like that. Some people prefer the more, the less constrained, less stressful structure granted by online courses. Anyways, So we can prove that this argument is invalid with the following interpretation. If we assign false to P and Q, but true to S and T, we get an interpretation or a truth function where the premises are true and the conclusion is false. Now, we haven't proved that our system will only prove correct, semantically correct things, but we can reinforce our syntactic intuition. I mean, discipline is just a general need in life, especially in a world as complex and sadly malicious and antagonistic as ours. If you don't internalize discipline, the world is gonna carry you as a wild raging stream drags people down. So yeah, this exercise is impossible. It cannot be proven. This argument is invalid. Then we have this, which is a fairly standard exercise. Yeah, Katsuragi's words. Yeah, in the words of the great Kim Katsuragi, if you don't want to get your shit together, the world will move on and ignore you. So we want to prove P or S, the disjunction of P or S. We scan our premises. Okay, we have P as the consequence of 2. So if we can get T, we can get P. We can get T as a consequence of 1. Okay, if we can get R or Q, we can get T, and with that we can get P. So the goal of this exercise is to get people to slowly familiarize themselves in multi-step reasoning. I want P, so I want T. I want T, so I want this one. Okay, I have this one. I can start the machine. 3 is the antecedent of 1, which means I can use my conditional elimination of 1 and 3. So I can get T. T is the antecedent of 2, so I can get the consequent P by conditional elimination of 4 and 2. 4 and 2. And finally, once I have P, I can use disjunction introduction to get P or S, which is our conclusion, and that's it. The next exercise is basically the same, but a little more complex, because instead of individual letters, we have whole formulas. Other than that, it's really the same exercise, but with more steps. I want R or S. Okay, R appears in 2. Oh no, wait. I want P and Q and R. Never mind. So I want all of these letters individually. I want R. So if I want R, I need T or W. If I want T or W, I want R or S. I have R or S in 4. So I start with conditional elimination of 4 and 1. I get T or W. T or W is antecedent of 2, so I get R. And with R, I get P and Q by conditional elimination of 2. Oh, wait, no, right? Here, there's one. Conditional elimination of 3 and 6. 3, 6. There you go. Now that I have P and Q and R, I just put them together through conjunction introduction of 6 and 7. And that is it. I want not Q and not P. Okay, I already have not P as my premise number 1. So I need not Q. Not Q appears as a consequent of the consequent of 2. So I first need to break down this to get this part. which I do in 4, conditional elimination of 2 and 3, and then this is a conditional of which I already have the premise, so I have not q by conditional elimination of 1 and 4, and then I just join them together by conjunction introduction of 1 and 5. I need W if and only if T. So I can get that by two ways. I can either produce two conditionals or I can produce W and T. Well, turns out that getting W and T is rather simple. I can get T from 1. And I can get W from this formula. First I need this consequent, which I can just do because this is the antecedent of 3. The whole trick of this is to get more familiarized with the notion that we're not dealing with letters, we're dealing with formula. And as long as the pattern matches, as long as this is an antecedent and this is the same formula, I can do my rules. I can do conditional elimination. So because all of this is the consequent at the antecedent, at 2, I can get the consequent, and then once, because I already have S and T, I can get W, and once I have W and T, I can do disjunction introduction to get my B conditional. Another formula in which I have to build another argument, in which I have to build a series of conjunctions. So I need to get them part by part. Wait, no, I just need Q. I keep misreading this. I just need Q. In order to get Q, I need T and R and S. Okay, and in 3, I have W and R and S, so I start breaking them down. I first break down W and R because I can only... Because this is the main connective, I cannot directly jump to W. I first have to break down this part, and then from this formula I can get W. Once I get W, I can get P and T. So I just have a bunch of conjunctions, and I break down letter by letter, and I start building up everything I need to get this formula. So I have T and R, and then T and R and S, which is antecedent, so I can get Q, and Q is the conclusion. Okay, this one is also going to be useful in a bit. From not P and Q or P, obtain Q or R. So I have a disjunction. I have to use disjunction elimination. That means I have to analyze each part and get Q. So if Q, I already have Q. That's it. I got the subproof starts and ends with the same formula. From P, how do I get Q? Well, my other premise is not P. So if I have a P and not P, I have a contradiction, which I introduce by contradiction introduction by 1 and 4. And from that, I can extract any formula I want, which in this case is Q. And therefore, I can obtain Q by disjunction elimination. Which disjunction? The 1 and 2. The first subproof of the first disjunct goes from 3 to 3, and the other one goes from 4 to 6. And once I have Q, I can just add Q or R by disjunction introduction at 7. And that is the homework. Again, it's a bit difficult for me to not immediately see how to do them, because I have literally done this shit for over... I started studying logic in 2010. So yeah, 15 years. I have been doing this shit for 15 years, so at this point my brain is just completely automatized. I don't need to think, it just does it all by itself. Really, really some Bruce Lee shit. Now, the point of this is not to just prove arbitrary arguments. That is a pure exercise. That is purely for people to get conditioned into thinking this way, into mastering our deduction system as if it were a game. There's not a lot of mathematical merit to doing this kind of exercises. They're just that, exercises. The goal of them is not to prove anything important or relevant. The goal of them is to get people into thinking in a certain way. And why do we want to think in a certain way? Okay, because if you want to actually think and do mathematics, and I hope that at this point we all understand that mathematics is not really just about numbers. I mean, I don't want to disparage or disrespect number theory. Number theory, arithmetics is great. We obviously use arithmetics all the time in our daily lives. We use arithmetic to count our money. We use arithmetics to make basic calculations about how much stuff we need when we want to paint a wall, when we want to decide how much to cook, and so on. But most mathematics is not really about that. Arithmetic is, for most ordinary people, already solved. Real mathematics is about studying structural relationships between timeless concepts. And again, I hope that at this point we all understand that timeless concepts does not mean that I am glazing them, that saying, oh, they're great and timeless. No, I just mean that these are concepts that by stipulation do not change over time. Which creates a particular type of thinking. In this particular type of thinking, the kind of things that people who see the world through mathematics do is search for structures, relationships, and patterns that can be identified. And once you identify them, you can do math with them. You can play with them. You can easily explore the consequences of set structures once you learn to spot them. One of my favorite or easier to understand examples is when someone tells me that something is transitive. They don't need to explain much. They just tell me, oh, okay, this thing, oh, it's transitive. Okay, I get it. And I immediately know how it works. Because the underlying abstract structure, which is pretty general, I already know what it is. So it immediately clicks. I already know what a transitive property is. So once someone tells me, oh, this is transitive, okay, I already know what you can do with it. The transitive property, when something, a mathematical operator or whatever has a transitive property, it just means that the property carries along. It is that simple and yet that abstract. We will prove that the conditional, let me copy paste the symbol. We'll prove that the conditional has a transitive property. So, because this is a general theorem, we are not going to start with any premises. Eventually, what we want to prove is that if A implies B, and B implies C, that means that A implies C. And in this case, A, B, and C are metavariables. I'll just use under lowercase letters because I don't want to copy and paste the Greek symbols all the time. Imagine this is an alpha, this is a beta, and this is a gamma. Again, it doesn't really matter what symbol I use, but at this point, when I tell you, oh, I'm going to use these symbols as metavariables, that should be enough. Because again, a metavariable is another interesting mathematical property or concept that we wish, that's the real point. That people, I just need to tell you, oh, this is a metavariable, and you immediately go, oh, okay, I get it. So we need to prove this. So in order to prove this, which is a conditional, we start with a subproof. So this is the antecedent, and we need to prove this. A implies C. So we get by hypothesis. And I'm gonna open another subproof, which is just A, because I want to prove a conditional inside the conditional. So I need to get to C, which is, at this point, pretty simple. I just break down the conjunction at 1. So if I have A and A implies B, I have B by conditional elimination of 2 and 3. And then I have C by conditional elimination, this time of 4 and 5. Okay, we already have C, so I just need A implies C by introduction of the conditional of the subproof that we opened at 2 and ended all the way at 6, and that is exactly what we needed. So I can conclude this by introduction of the conditional of 1 all the way to 8. So yeah, that's it. It is that simple. When an operator or concept has a transitive property, that means it just carries along. If the first one goes to the second and the second goes to the third, and the operator has a transitive property, you can go from the first to the third. Or any, really. Think of it like a domino chain. If you drop the first one and they're all connected, if you drop the first one, that makes it so all the subsequent ones fall down. For example, being older than, it has a transitive property. So if Albert is older than Beth and Beth is older than Charles, then Albert must be older than Charles. Being older than has a transitive property. Some people, particularly people who like sports, have trouble understanding this. Because they believe that beating a team is transitive. but it's not. If team A wins against team B and team B won against team C, does that mean team A will win against team C? No! Winning is not transitive. First of all, because winning is not a formal property. It's not something we can define and analyze mathematically. Second, because we just have a vast number of counterexamples. But people, particularly sports baller fans, fall into this fallacious reasoning all the time. Year after year. I don't get it. Another example that is going to be actually useful. Sorry, greater than. Greater than is transitive. If A is greater than B and B is greater than C, therefore A is greater than C. This works under standard arithmetic. So see, the point of all this is not just making these proofs. The point is that through these proofs, we can have a greater familiarity of concepts that are useful for all mathematics. So hopefully at this point, once someone tells you, oh, X is transitive, that means you already know how it works. Or at least one very important property of that operator. Now let's prove indirectly that the biconditional is also transitive. For that, I'm going to prove something else first. I'm going to prove the biconditional elimination 2, or version 2. So I already know that a biconditional is two conditionals. So if I have A, and A if and only if B, I should just be able to get B directly, no? I mean, yes, but I'll have to prove it. So I have to prove this formula. So I want to prove this. So I start with this as hypothesis. This I get from conjunction elimination at 1. And then I get, let me copy my symbols. A implies B and B implies A. This I get from biconditional elimination. Oh wait, no, I can't because I first need to I jumped the gun, I jumped the gun. See what I mean? Once you're ready, your brain kind of does it for you. I first need to be extremely thorough and get this formula as well. And now that I have this formula, I can do biconditional elimination of 3, which nets me 2 conditionals of which I only need the first one by conjunction elimination 4. And if I have A, and if I have A implies B, I get B by conditional elimination of 2 and 5. And thus we have concluded that from this formula, I can get B. And I have that as a theorem by conditional introduction of 1 all the way to 6. There we go. Now, if I really want my life to be easy, I also need to prove the other one. But the wonderful thing about working with computers is that I can just copy and paste. And I will just replace it is completely symmetrical. Once I prove one side, I have essentially proven the other. I just need to copy and paste and change specific things. So once I have both sides, once I have both of these theorems, I now have the second version of the biconditional elimination. If I have a biconditional and I have one of the sides as a formula, as a premise, or whatever, if I have one of the elements, one of the connected parts in my proof, I can just get the other one. Either side works. If I have the first one, I can get the second. If I have the second, I can get the first one. That's it. And with this rule, it is extremely trivial to prove the transitive property for the biconditional. Trivial in mathematics is fancy word for saying this is very simple and I don't want to do it, but I'll do it anyways. So the transitive property for the biconditional is that if I have this and I have this, and I have this. It's a bit tedious, but some tediousness is good for the mind. Just raw work. Work. Elimination of the biconditional version 2 applied to 1 and 2. No, wait, no, not yet. This is just conjunction elimination of 1. Now I do that. So I can get B. And not from 1 and 2, but from 2 and 3. And once I have that, okay, no, I still need to do the full work. By conjunction elimination of 1. Now I can do this by elimination of the biconditional version 2 of 4 and 5. And thus I have proven that A implies C by introduction of the conditional of 2 all the way to 6. And now I have to do the same thing, which is perfectly symmetrical, but starting with C. This I get by hypothesis. This I get by conjunction elimination, but I don't need that one. I need this one. This lets me get B by elimination of the biconditional version 2 of 8 and 9. Once I have B, I'll just get this. And once I have this, I can get A by, once again, biconditional elimination version 2 of 10 and 11. And then in 13, I finally have C implies A by conditional introduction of 8 all the way to 12. And then once I have two conditionals, A and C, and A implies C, and C implies A, by introduction of the conjunction of 7 and 13. Finally, still within my first hypothesis, I have A if and only if C, by introduction of the biconditional at 14. And finally at 16, my theorem that the biconditional, surprisingly, is also transitive. And look, this is a very elemental level. And cognitively, this proof is very simple. But again, what we're doing here is not prove conjunction elimination, is so you can prove each statement separately, right? Doing the internal refresher. Yes, exactly, Rupert. Exactly. I cannot access this formula directly because this formula has as main connective this conjunction. So if I need to work on the constituent parts, I need to separate them. Yeah, don't worry, and feel free to ask questions. That's what we're here for. By introduction of the conditional of 1 all the way to 15. Okay, so yeah. This, what I just did here, is like riding a bicycle with wheels, but for mathematics. this is the kind of work that real mathematics is engaged with. Carefully defining and studying a property and then proving that the property applies. And also notice that I first prove something, my second version of the biconditional elimination, and once I know that that works, that is a theorem, because we are in an unchanging, timeless system, once I have proven this is true forever in my system. It's not true in any meaningful or interesting way, but it is true forever in my system. I will always be able to use this as an explanation. Okay, someone asks me, hey, what do you mean you can do this? Okay, just imagine that instead of doing this, I just did this. And that's it. I already did once. Exactly. I already did once, and because it follows from the axioms, I can just do it forever. So there's no need for me to do it over and over and over again. I already did it. I already proved this forever. And I have also proven forever the transitivity of both the conditional and the biconditional. Now, if we put these two results together, the transitivity of the biconditional and the second version of the biconditional elimination, imagine we have a chain of biconditionals that go all the way from A to Z. And we can go even further. We can go like an arbitrarily large number of letters. So this is, we can just go from Z, and then from Z we can go to Y 1000 to C 1000. So imagine it is an arbitrarily long chain of biconditionals. I know that A is true. I know that the biconditional is transitive. And I know that if A is true, the consequent is true, or the other part is true. So if A is true, then B is true. If B is true, then C is true. If C is true, then D is true. And so on, all the way in an unbroken chain from A to C 1000. Such that if I were to build a chain of transitive elements, and if I were to prove the first one, just like a domino, like a chain of dominoes, I will prove all of the rest ones, all of the remaining ones. Does this make sense? Because this is very important. This is extremely important. Once I have proven that certain elements in a mathematical arrangement are transitive, and I can build a straight line from the first one to the last one. Yes, exactly, Rupert. Exactly. This is backwards recursion, also known as mathematical induction, which is a technique necessary to prove an infinite amount of things. The transitive induction of redstone. Yep. Exactly. Yes. Yes. I mean, the thing is, redstone is never infinite. It can just be arbitrarily long. Mathematical induction can prove things in really infinite sets. Okay, we're not going to do mathematical induction just yet. The important part is, once we understand two basic ideas or two basic concepts, for example, the transitive property and our consequence rule, modus ponens or biconditional elimination, with just those two ideas, we can start building an infernal machine that can conquer the infinite. So one of the bedrock properties to understand and be able to prove sets and formulas in myriad ways. Yeah. The transitive property is indeed incredibly important. It starts out simple. Yeah. If there's something in mathematics worthy of being called the infernal engine, it is mathematical induction. Now, this is not mathematical induction, okay? Because this is still, after all, a finite amount of steps. This is merely a hint of the real mathematics that await us if we keep going. Again, my point in all this, my goal in all this is not to get people just doing exercises for no reason. The exercises are good. I recommend doing the exercises. They're good for your brain. But the point of all this is that this is a way of getting closer to understanding how real mathematics are done and how mathematics works in a meaningful sense. Okay, let's prove another bunch of interesting things. Okay, another classic rule, one that I absolutely love. So we have modus ponens, or elimination of the conditional. So modus ponens is the classic if P, therefore Q, P, Q. The most basic ass example of what a logical rule is. But then we have the Wario to the modus ponens, modus tollens. Okay, Rupert, I think you paused that in the wrong stream. Oh no, wait, because never mind. I get it now. Well, yeah, do go follow Complain Laney. Let me give a shout out. Great comrade, part of TankyTube. In fact, I just link you to TankyTube. Sorry, TankTube on Twitch. Bug helps us understand both Moses. Bashira, yeah, Bug is great. I seem to have forgotten where to get the link. There we go, found the link. Yeah, a bunch of good comrades with quality streams over there. Okay, so where were we? Oh yeah, the Wario of the modus ponens, modus tollens. Modus tollens is short of modus tollendo tollens. If modus ponendo ponens was a way of affirming by affirmation, modus tollendo tollens is the mode of negating by negation. If P implies Q and not Q, then by necessity, not P. And we're going to prove it as a general theorem. So we have A implies B and not B. That implies not A. Is there a way to affirm by negation? Not in classical logic. And not with the conditional. Affirming by negation will be saying this. And that's a fallacy. That doesn't follow. The way the conditional works, you can only affirm by affirmation or negate by negation. And that's it. So as usual, we start with a hypothesis. In another logic I see, I mean, the terms modus tollendo tollens and modus ponendo ponens were invented by medieval monks and other nerds who basically were professional debate bros. And they saw the same patterns in reasoning so frequently that they just decided to make a taxonomy of them. And that's where a bunch of the names of these other rules come from medieval scholastic debate bro teams. As my teachers say in a very boomer-like manner, well, there was no TV back then. And they were monks. So the other fun thing you can do without TV was legally, officially, out of the question, but who knows? So elimination of the conjunction of one. Not B by elimination of the conjunction of one. And then we need not A. In order to get a negation, we start another hypothesis, another subproof inside the subproof. We have B from conditional elimination of 2 and 4. Do we all see it? In 2 we have the conditional. In 4 we have the antecedent. So we can get B. But oh no, tragedy! We will have B and not B. Where's my logic symbols? So by introduction of the contradiction of 3 and 5, which is B and not B, and then in 7, because A led me to a contradiction, that must mean that not A is true, by introduction of the negation of 4 all the way to 6. Debate, bro. Yaoi visual novels are on tap market too. Is it Tornadoes a good job of it already? Exactly. Exactly. If you want to see me and a comrade play through Debate Pro Yaoi visual novel, you can check out Futakuchi Mana's channel. Last year, we played through Socrates Jones' Pro Philosopher 1 and 2 in her channel. Let me link that as well. Particularly, check out the subathons. I mean, Pebbles and I, that's a comrade, appear on those. Anyways, back to the mathematical work, because we have not A, and that means we have basically finished. And we can affirm this because of introduction of the conditional from 1 to 7. So to recount the general proof for modus tollens, we can conclude the negation of the antecedent because we're in a bivalent logic. Something either is true or false. So, because the consequent is false, if the antecedent were true, we will have a contradiction, because antecedent will prove that Q. But we have not Q. Therefore, in order to block the contradiction, we get that not the antecedent, and thus we have modus tollens. Okay, let's prove a couple of really... Yeah, thanks for the son of a stretch. Let's prove a couple of relatively simple ones. Idempotence means same power. Idempotence. Basically means Yeah, you don't need to do anything. They mean the same thing. It is trivial and unnecessary to do this because the same. The proofs of this are trivial. I'll do them anyways because we're obsessive. So we want to prove the idempotence of the conditional. We need to prove that A if and only if A and A. So that's the fancy for proofs. The fancy way of saying it is proven, it's called QED, which is short for quod erat demonstrandum. Which is a very annoying phrase that only the cringiest people use. Because no, I mean, really, what need is there to speak in Latin anymore? Like, to use these fucking fancy-ass Latin terms. Yeah, again, in the medieval scholastic traditions, where people were professional debate bros and just debated theology for hours every day, once someone had finished their proof, they would end with "and quod erat demonstrandum," basically meaning, yeah, what was meant to be demonstrated. Or, I have proven it. Bachelor from pathological behavior, yes. Some people who study logic and learn this term, they later use QED or quod erat demonstrandum in online debates, and I want to pull my eyes out whenever I do that because it's just so unbearably cringe. Anyways, let's prove this. So we need to prove this. So hypothesis A. Introduction of the conjunction of 1 and 1. A. Hypothesis. A. Elimination of the conjunction of 3. Oh no, wait, I fucked up. They are separate subproofs. So I have this. I have therefore that A implies A and A. And in 6, I have the inverse, that A and A implies A by introduction of the conditional of 4 to 5, and here by the introduction of the conditional. Die, monster, you don't belong in this chat. It was not by my hand that I am once again given an account. I was brought here by scammers who wish to give me tribute. Tribute? You steal people's accounts and make them your slaves. Perhaps the same could be said of all grifts. So we have introduction of the conditional by 1 all the way to 2. And then in 7 I have by introduction of the conjunction of 3 and 6. And finally in 8 I have the actual formula, introduction of the be conditional at 7. As I said, pretty trivial, not much. A lot of interesting cognitive moments here. Just, yeah. A means the same as A and A. Just repeating something does not make it more powerful. Likewise, the proof for the idempotence of the disjunction is trivial. I'm not gonna do it. Yeah, that is the goal, Rupert, don't worry. Okay, let's do something interesting. Oh yeah, disjunctive syllogism. So we have that A or B, and we have that not A. We have B. Very simple rule. Basically, you go to a restaurant and you ask, hey, what is there to drink? And they say, well, we have horchata or Jamaica, but we ran out of horchata. Well, that basically means Jamaica. If there's only two options and one of them is not available, then the other. But even though it is intuitively simple, we still need to prove it. So again, we need to put this into our theorem schema. A or B and not A. Implies B. And of course, we start with opening a subproof, doing a hypothesis, then breaking down the conjunction into parts by elimination of the conjunction into one. Elimination of the conjunction of one. And then we want a B. Okay, we have a disjunction, so we have to do disjunction elimination. So we do another subproof inside the subproof. The first part is A. But hey, we already said that A was not available, not A, in 3. Therefore, we immediately introduce a contradiction between 3 and 4. And then that allows us to extract any formula we want, in which case is B, by elimination of the contradiction of 5. So that is the first subproof. Then we open another subproof that starts with B because it's the second disjunction. And from B, we have arrived at B. Yay, we immediately open and close this subproof. So because A or B is true, and A took us to B, and B took us to B, we can therefore conclude B by elimination of the disjunction that is at 2, with the first subproof being from 3 to 6, and the second subproof being from 7 to 7. And from that, we can conclude our theorem by introduction of the conditional from 1 all the way to 8. And so we have another rule for our system. This is called disjunctive syllogism. Or DS. And that gives us another way of analyzing disjunctions. Okay, another interesting rules are commutation and associativity, which are actually very useful for math in the arithmetic and algebra levels. Commutation basically means that the operation, I'm going to use this symbol for any operation, just like whatever, is symmetric. Basically, it doesn't matter if it goes A operation B or B operation A. For example, sum is commutative. 2 times 3 is the same as 2 times 4. Minus is not commutative. 2 minus 3 is not the same as 3 minus 2. And the reason why PEMDAS exists depends a lot on which operations are commutative and associative. In mathematics, when people say does not equal, they tend to use the exclamation sign like this. This basically means does not equal. 2 minus 3 is minus 1. 3 minus 2 is 1. 1 is not the same as minus 1. But the sum is commutative. Yeah, it's fine, don't worry. 2 plus 3 is 5. 3 plus 2 is 5. Therefore, they are commutative. So we're going to prove that actually multiplication is commutative. 2 times 3 is the same as 3 times 2. Because multiplication is just a sequence of sums. Because we can break down multiplication into sums, all of the properties of sums apply to the properties of multiplication. Why do you say that? Brain fart, it happens, it's fine. But see, even though this is extremely simple, this is real math. Real math is not so much about multiplying the numbers. I mean, that is math, that is useful. But the real fun stuff is this. Is exploring this property and generalizing in a very highly abstract way. Okay, so in our system, conjunction, disjunction, and biconditional are commutative, which means that A and B is equivalent to B, B and A. A or B is commutative, which means that B or A is the same as A or B. And yes, the B conditional is also commutative, which means that A if and only if B is the same as B if and only if A. These are, again, extremely trivial, except the second one. The second one is the only... No, they're all trivial. They're all trivial, but fuck it. I mean, we have to do them. This is the least trivial one, and therefore the most tedious one. Okay, and that is it. By elimination of the disjunction that starts at 1, the first subproof that goes from 2 to 3, and the second subproof that goes from 4 to 5. Therefore, in 7, I get an A or B implies B or A by introduction of the conditional from 1 to 6. Now, is it necessary for me to do the other half? The other half is exactly the same because they are symmetrical, and we're trying to prove the symmetry of the connective. I mean, I can do the same, but okay, fuck it, I'll do it. But it's basically a copy and paste. It is symmetrical. Commutativity is a symmetry of a connective, so I just do the same, except I change the numbers. And this time it's B or A. Again, I'm really thankful that I can do this with my computer, because by hand is just pure pain. From 9 to 10, from 11 to 12. Finally, this from 8 to 13. And in 15, can just do this. And I can do that by introduction of the conjunction of 7 and 14. And finally, in 16, I have my formula. By introduction of the be conditional at 15. And thus, I have proven that the disjunction is commutative for propositional logic. Not surprisingly, the conjunction and the be conditional are also commutative. The proof, you can do that by yourselves now. Another interesting and very useful property is a commutative property or commutation. And likewise, it applies to the same three connectives in our propositional system. Squats! Stretch, stretch, stretch. Get some fluids into the knees. Assume the squatting position. And ass to grass, let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My knees thank you for the increased blood flow. Okay, so what does commutation mean? Commutation means that A and B and C, let me put it in lowercase, easier to read. Is the same as A and B and C. So basically, we can shift the parentheses around. A sequence of 3 conjunctions is the same no matter the order of the parentheses. And this applies to disjunction, and this applies to be conditionals. When a function or an operator is both commutative. No, wait, this is not commutation, this is association. We just proved commutation. Association. There we go. When an operator or function is both commutative and associative, then and only then do we say el orden de los factores no afecta el producto. The order of operations does not alter the results. I never liked that phrase. Like, people in my math classes in middle school and high school, they say that phrase, but I never understood the context behind. That's because I'm autistic and I needed to be told what it means exactly. Okay, this is what it means exactly. When an operator, you can say that the order of operations does not alter the result, it means that it has both the commutative and associative properties. Basically, what this means is that A and B and C and D and E and F, and so on. If I only have one type of connective, I don't really need to bother with parentheses in this point. Okay, in basic arithmetic, sum and multiplication are also associative. So 1 plus 3 plus 4 is the same as 4 plus 1 plus 3 is the same as 3 plus 1 plus 4, and so on. Do keep in mind that association and commutation, what will division be called? It's not what they're called, it's a property they have. It's not that we're calling the multiplication associative, it's that it has a property, the property of association. But the sum is sum and the multiplication is multiplication. They do different things, even though we can define the multiplication in terms of the sum. At least in arithmetic, then yeah, it gets weird. It gets really weird. What property will division be called? I am not sure what properties we can say of division. I mean, we know that division is not commutative, nor is it associative. The order in division matters a lot. Okay, we are 15 minutes away from the 2-hour mark. Let me see what other very important secondary rules we need. Okay, transposition. Transposition is also a good one. It's one I use fairly often. Whoops. Oh no. Unicode. But it's fine. I know transposition by heart. Distribution from Biscay Post. The distribution rule is not that one works very well for sets and for Venn diagrams. Transposition is a bit more important. I mean, well, let's do both. I think we have time for both. Let's do as many as we can. Okay, so basically what this means is that A implies B is equivalent to not B implies not A. Whoa, how do you do that? I. I like this rule a lot because it helps me clarify what a lot of people are saying when they use conditionals. I actually use this one a lot in like understanding speech. Universes of sets and such. Yep. Yeah. So yeah, this one is pretty simple because we have already proven modus ponens, modus tollens. My bad. So we open to subproofs and then immediately by modus tollens or MT, between 1 and 2, we get not A, and introduction of the conditional from 2 to 3, and thus we have the first half, introduction of the conditional from 1 to 4, and then I immediately open another hypothesis, another self-proof. And then another one, and then this time I assume A, hypothesis. And this time I will use my double negation rule at 7. So I can use this rule. Not A and not A. So not A is a negation of not A. That means I can use modus tollens to get the negation of this. The negation of not B being not B. Modus tollens by 6 and 8. And then in 10, I get by double negation of 9B. And then in 11, I can close this subproof because I have gotten that A implies B by introduction of the conditional of the negation. No, wait. Of the introduction of the conditional, sorry, brain not braining, from 7 to 10, and then in 12, I get that not B implies not A implies not A implies not A implies B. By introduction of the conditional from 6 to 11, and then in 13. Okay, this point is just mindless drudge work. We've done this literally dozens of times by now. Whenever I have two conditionals in this structure, such as the first one implies the second and the second one implies the first, I can join them by introduction of the conjunction of 5 and 12, and then finally in biconditional form by introduction of the biconditional of 13, and that's it. So a lot of times when people say by converse or by transposition, they mean this. If this were to happen, then this will happen. Oh, so you're saying that in the converse, if that doesn't happen, then the first one will not happen either. Oh, I see. I understand. It just tells us the same thing, but in a way that is sometimes easier to understand. That's it. That's really all there is to the rule. Okay, so distribution. Distribution is very useful if we actually start working with sets or with Venn diagrams. Distribution. Oh my god. Unicode once again. So it is conjunction over disjunction. Okay. A and B or C is equivalent to A and B or A and C. Okay, what does this tell us? This tells us, okay, because we already know that A is the case, and we have that B or C, well, that just means that A and B or A and C. The reason why I said this is very useful for Venn diagrams. Let me see if my LibreOffice powers. Good enough. Oops. I wonder if there's a way to make them transparent. Yes, okay, well, we'll do. We just free draw tools. Okay, perfect. So my end, the red one is A. Oh my god. The blue one is B. And the yellow greenish one is C. We already know that we live in a world with A. That's because A is affirmed with a conjunction. So we already know that we are in A. All of this, all of the world outside A, nah, doesn't work. We're inside A already. So we can ignore all of this. Everything outside A, we don't care. Because we are already in A, and either B or C, then that means we're either here, here, or here in the middle. That's it. That's really what that rule says. This spot is A or B. This spot is A or C. This spot is A and B and C. I hope the drawing helps. And that is, I think, where the distribution property came from Venn diagrams. Okay, but that was just a visual exploration. We need to actually prove it. So, as always, we start by assuming the first part through hypothesis. Oops, what happened? By elimination of the conjunction in 1. That's the most bent ever diagram. Hopefully. And then we have B or C. Likewise by elimination of the conjunction in 1. And then we do a hypothesis another subproof with B, because we're going to do disjunction elimination. And in 5, we have A and B by introduction of the conjunction of 2 and 4. And in 6, we have this by introduction of the disjunction of 5. We close that subproof, we immediately open another, this time with C, and it is the same thing except it is A and C by 2 and 7. So in 10, because B led us here and C led us here, so they both led us to the same place, and at least one of them has to be true, by elimination of the disjunction of 3, with the first subproof going 4 to 6, and the second subproof going from 7 to 9, we can prove this. And that is the first half. So we get this whole chorizo of a formula, except it only goes in one direction, by introduction of the conditional from 1 to 10. So I then open another subproof. This time I assume the other half by hypothesis. And because the only thing I have to work with is a disjunction, I immediately set to do another disjunction elimination. So the first disjunct is A or B. Hypothesis. So I need to get A or B or C. So A and B or C. So I need to break them down by elimination of the conjunction at 13. 15, B, by elimination of the conjunction at 13. In 16, I build B or C by introduction of the disjunction of 15. In 17, I build A, basically, yeah, this formula by introduction of the conjunction of 14 and 16. Close this subproof, and then I open another one which is fairly symmetrical, which means I can just copy and paste, except this time it's A and C. I change the relevant numbers. Except I need to actually update them. This one, this time is 20, and this time it is 19 and 21. And so in 23, in this subproof, I can assert that A and B or C by elimination of the disjunction that is a 12, with the first subproof going from 13 to 17 and a second subproof going from 18 to 22. And that means, because in 12 I assumed this, and because in 23 I concluded this, through the rule of introduction of the conditional from 12 to 23, I can clone this, and in 25, I have both the formula that goes and the formula that comes. And just need to paste them into a massive chorizo of a formula. It's so big that it doesn't even fit in my page. My introduction of the conjunction of 11 and 24. And that means that finally in 26, I can finally conclude the distribution of conjunction over disjunction. By introduction of the biconditional at 25. Oh boy! Okay, so why did we do all of this for? One, because it's exercise. And two, because it familiarizes us with how mathematical proofs work. So far, all of the mathematical proofs that we have made have required no thought, no ingenuity, no creativity, just the mechanical application of very specific rules. Real math does require creativity and insight and a very keen understanding of the relationships at play. But that is the goal. So we start with baby steps, with simple, tedious but simple mathematical proofs. Now, there's not a lot of interesting properties left. Okay, there's two interesting ones. This is gonna be the homework. The homework is for you, people at home, to do the other distribution. The distribution of the disjunction over conjunction. Basically the dual of what we just proved. And another interesting property is Clavius, the laws of Clavius. It's fine. I will appreciate it if everyone did the homework because, again, just knowing isn't enough. You need to change how your brain works in a fundamental neurophysiological level. So, okay, negation implies if a formula implies its negation, then the formula is false. And the converse, which is if a negation of a formula implies the formula, then the formula is the case. So yeah, all of these three exercises will be the homework. Now, usually in a Logic 101 setting, we will spend an entire month just doing deduction. And that's because we really want people to like get into this. Doing them through the same computation methods and rules? Yes. The 12 basic rules and any of the ones we have proven so far in these last 2 sessions. So yeah, in a normal course, we will do this for a month, and that will be an entire semester of Logic 101. So next session, we will go over our 2 notions of logical consequence. This is just a sneak peek for the boys. Ah, damn you, Lattics! We will go over 3 funny results. We will show that for propositional logic, logical consequence matches with proof. And we will go over something called the meta-theorem of deduction, which is something as cool as it sounds. I mean, it is cool for me. And with that, we will be done with propositional logic. Depending on how well we go over this, we will start actual real logic, which is first order logic. Anyways, I know today was a tough session, but it's necessary. I hope that nevertheless you all had a good time. I'll see you next week. Have a very good time. Bye bye.